and a lot of properties of graphs. We're going to have several functions that we see very frequently in this. And those are going to be, when we get into transformations, we're going to use all of those for parent functions. You've seen most of these graphs before, but in Algebra 2, you mostly just did transformations with like parabolas and absolute values, and we're going to extend it and do it with a lot more functions. So today, we're just kind of introducing all the functions that we're going to be seeing frequently and talking about some of the properties of all of those different graphs. One thing that we're going to talk about is if a function is continuous. So there are a lot of properties that hold true at certain spots on the graph where it is continuous. And that just means that you can graph it without picking up your pencil. So if you were tracing the graph and you can trace the entire thing without picking up your pencil, then it is always continuous. Anywhere where you have a break in your graph or you have to pick up your pencil, we call that a discontinuity or a break in the graph. So for instance, if I looked at this graph, is that continuous? Can you draw that whole thing without picking up your pencil? Yes. If I looked at this graph, where is it discontinuous? Where do we have to pick up our pencil for graphing this? Yep, when I get to the y-axis. We normally will list it as like an x value, so this one is discontinuous when x is 0, or we could say it's continuous everywhere else. So you could say from negative infinity to 0, into its closed circle, so bracket, union, then start up at 0, and went to infinity. So we could say that. So let's practice looking at some graphs and giving the intervals where they are continuous. So if I look at A, it is very hard to tell, and I apologize for that. There is an open circle here at 0, 2. So where is this graph continuous? Has to do a parenthesis, has an open circle, union, and then after 0, we're continuous again, so 0 to infinity. So it was continuous everywhere except 0 itself. If I look at B, so it's zigzags. Could you draw that without picking up your pencil? Yes. So we would say this one is continuous from negative infinity to positive infinity. It's continuous everywhere. All right. C. Where is that one continuous? Everywhere except at 2. So to give me the interval, you would say negative infinity to 2, union 2 to infinity. And D, what is it? It's continuous everywhere. Does everyone understand what it means to be continuous when looking at a graph? The second property we're going to talk about today is increasing, decreasing, and constant. So we use these same terms in talking about lines. We said, if the line had a positive slope, it was increasing, a negative slope was decreasing. What kind of function was constant? Or when we're talking about lines, what does it take to be constant? no change. What'd that look like on a graph? Well, yeah, when there was no change at all. So that was a constant. So increasing is just like a positive slope, rising, decreasing is falling, constant is no change. Now, we can use these same terms. It doesn't have to be lines. It can be with curves. We just have to go from left to right. You do have to be a little bit leery. Sometimes people get confused if I gave them like this one and I put an arrow here and a closed circle here. They want to tell me that's decreasing because it's going down, but it's actually not. Why is that still an increasing function? Right. When you go from left to right, it's coming from negative infinity and going up. So the key to increasing, decreasing constant is from left to right. When I'm asking where things are increasing, decreasing constant, you will always give me the x value. So just like with continuity, we list intervals with our x values. We'll do the same thing here. The only time you're ever going to use y values in your interval is if you are talking to me about the range. Otherwise, we always use the x. Because a function, when I say x equals 4, that's only one spot on the graph. But if I said y equals 4, could there be multiple places on the graph when y was 4? Yeah, so it doesn't really tell me exactly where I'm talking about. Okay, so common functions. The first one that we look at is called the identity function. F of x equals x. What is that? Oh, come on, everybody knows what this graph should look like. F of x is the same thing as y. So if I say y equals x, what do I have? Yeah, 1, 1, 2, 2, 3, 3. It's just a line, isn't it? The y-intercept is 0. The slope is 1. Up 1 over 1. Or y and x are the same. 0, 0, 1, 1, 2, 2, 3, 3. So we have our graph here. Pretend my line was perfectly straight. It's a little bit wiggly. Domain. So as I'm going from left to right, what x values does this line hit? All of them. Negative infinity to positive infinity. Range. As I go from the bottom to the top, what y values do we hit? I didn't ask, but is this function increasing, decreasing, or constant? Increasing from negative infinity to positive infinity. If I asked, where is it continuous? Yeah, it's continuous the whole time. So kind of uninteresting in that point. Everything's negative infinity, positive infinity. All right. The next one, the square function. F of x equals x squared. What does that look like? A parabola. My general rule is you have to have a minimum of 3 exact points. So if I'm going to look at this, we have to have exact points. You can make a t-chart if it helps you to write them down. If you don't want to write them down and you just want to plot them, that's okay. I'm not necessarily checking if you have a t-chart out to the side. I'm looking at your graph and seeing if you have points plotted. So if we put in 0, 0 squared is 0. 1 squared, 2 squared, negative 1 squared, negative 2 squared. All right, let's plot what we've got. 2, 0, 1, 2, 4, 1, 1, negative 2, 4. If I did 3. 3 squared is 9. Negative 3 squared is 9. So more points than I have to have, but let's fill up my graph. So I get my parabola. Domain. My possible x values. As I go from left to right, what am I hitting? Range, my y's, as I go from the bottom up.
0.
Alright. Where is this graph continuous? Negative infinity to positive infinity. I can draw the whole thing without picking up my pencil. What if I asked about increasing, decreasing constant? What's happening on this one? Is it just one thing? No. What's my graph start out doing?
Decreasing.
So we could say it's decreasing from negative infinity to 0. Okay, little side note. Technically on the 0, it doesn't matter if you do a parenthesis or a bracket. Reason, at a single point, you're not going up or down. So you could include it, you could not. I think when we do Math Excel on these, the Math Excel will always say give the open interval where it's increasing or decreasing. Open interval meaning everything's parentheses. So I'm going to do parentheses because when you get to the Math Excel, that's what it's going to ask for. But on a test or quiz, it actually doesn't matter. It's just a matter of what textbook you're using, which notation they use. So I would accept either there. So it's decreasing from negative infinity to 0, and then what does it start doing after 0? So it's increasing from 0 to infinity. All right. The cube function. F of x equals x cubed. What is that? You guys remember?
I know what it's called.
You know you've seen it before. It's kind of familiar.
It starts from the bottom and does a little.
Uh-huh. So if we aren't for sure, and you know I'm going to ask for a minimum of 3 exact points, what should we do?
T-chart.
Make a T-chart. All right, so if we do that, we can plug in some positives, some negatives, and 0. Let's do 0, 1, 2, negative 1, negative 2. So 0 cubed is 0. 1 cubed, 2 cubed, negative 1 cubed, and negative 2 to the third. So if I plot those. 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative. Kind of missed my point there. So it should look like this. Domain. As we go from left to right, what do we hit? Range. Is this increasing, decreasing, or constant? And you could actually go ahead and put those together. So it flattens out at 0, but it never actually switches direction and goes down or turns flat. So we could just say it's increasing from negative infinity to positive infinity. All right. Square root. guys remember, have you seen this graph before? Talked about it? Maybe, maybe not. What kind of numbers can you do the square root of? Perfect squares will give us the nice points. Technically, the non-perfect squares just have a square root. We just probably don't want to graph them because they're not very friendly. So if I make my t-chart, we would prefer to put in perfect squares. So if I put in 0, square root of 0 is square root of 1. Give me another perfect square. 4, square root of 4. Another one. 9, square root of 9 is 3. Can I put in negatives? Why? Yes. If you put in negatives, they give you imaginary numbers, and we are only graphing real numbers here. So 0 is the smallest thing we can put in. 0, 0, 1, 1, 4, 2, 9. Domain. And we do a bracket on the 0. Range. And we have a bracket on the 0. On this graph, you could also say it's increasing from 0 to infinity. It's continuous from 0 to infinity. All things happen from 0 to infinity on this. Alright. Why don't you guys see if you can get the graph of the cube root? So take a second, see if you can figure out some points to plug in. So we want to put in perfect cubes, things we can do the cube root of. If you put in 0, you get 0. Cube root of 1 is 1. What's another we can put in? 8, 2. Can you do the cube root of negative numbers? You can't do the square root, but when you cube a negative, can you get a negative answer out? Yes. So we can do the cube root. If you weren't sure, grab a calculator. If you type in the cube root of negative 1, it doesn't tell you domain error. It tells you the cube root of negative 1 is negative 1. Cube root of negative 8, negative 2. Get something like domain. Range. Is this graph increasing, decreasing, or constant? Increasing the whole time. And it is continuous, no breaks in our graph. Absolute value function. This is another one that you definitely did a lot with in Algebra 2. So if we plug in points, absolute value does what? Makes a V. Whatever you put in, it just gives you the positive of that number. So if you put in negatives, you get positives. If you put in positives, you get positives. So 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. Domain of that? And the range. have to have a bracket because we do hit 0, and then everything above it. Any questions on those? Last one I want to look at today. I want to graph x equals y squared. How is that different from my others? Yeah, we flipped the x and y, didn't it? All the others were y equals. This one is x equals. Now, if you're trying to get the graph, a t-chart is still helpful. But would it be easier to plug in numbers for x or y this time? Probably be easier to plug in something for y, and then I can square it and get my x out. So when we put in points, I'm always having you do zeros, some positives, and some negatives. So let's try it. 0 squared is 0. 1 squared is 1. 2 squared, 4. Negative 1 squared is positive 1. Negative 2 squared, positive 4. Let's plot them. 0, 0, 1, 1, 4, 2, 1, negative 1, and 4, negative. What is the domain of this one? What is the range? Is this a function? No. Why? It fails the vertical line test. We can draw vertical lines and hit the graph multiple times, so definitely not a function. Could you tell me increasing and decreasing on this? Not really. If I start going from left to right, half of it's going up and half of it's going down. We reserve the increasing, decreasing constant. We only use those when we're talking about functions. If it's not a function, we really can't do that. All right. We are going to save the last part of this, the symmetry, for tomorrow. So if you look on Google Classroom, there is a handout for you with just a lot of questions about these common graphs. So you've got quite a bit of time right now to work.